So in the last lecture, we discussed two things. One, we stated that the wave function psi of the particle in a box was given by root over of 2 by L, and there was a sine function. Okay, so there was a sine n pi x by L, and you see the probability, which is nothing but mod square of psi. Okay, the probability was a function that depends on the square of sine. Okay, so this thing is also easy to see. Now without doing much more mathematics, okay, without doing much more mathematics, what I did is I drew the graph of this diagram, and I stated the probability at various values. So I stated the probability at n equals to 1, and I said that most of the time the electron spends at the center. Then I also stated the probability of 2 just by drawing the diagram of sine square n pi x by L. So for n equals to 2, I drew the diagram of sine square 2 pi x by L, and I stated that at the center the probability of finding the particle is 0. It means the particle is never found at the center. Okay, these things were discussed in the last class. Now I wanted to show mathematically that for n equals to 1, the fact that most of the time the electron spends some at the center of the box is true. So let us see mathematically. So what do you remember the expectation value of x? So what was the mathematical definition of expectation value of x? You need to integrate from where to where. You did an integration from the entire space. Here the entire space means from 0 to L, because we are not considering any space beyond 0 or beyond L. And then there will be a psi star. This was the definition. Okay, and this definition, from where we got this definition, was also discussed. Okay, so psi star x psi dx. Okay, so what calculation, what mathematics do we need to solve? We have integration from 0 to L. Since psi star is equals to psi, because this is a not complex function, so we have x, and we'll have sine square n pi x by L, and there will be a 2 divided by L. Agreed? Now how to solve this? Well, just let me give you one step. Okay, the next is your work. So 2 by L integration from 0 to L. Okay, so break the sine square into cos. So that will be 1 minus cos. So what is there inside? So cos n pi x by L. Okay, so 1 minus cos this much whole divided by 2 into dx. Okay, this is how you need to solve the integration. So next step will be, so keep the 2 by L outside as always. Okay, so the first term will be so the integration of x, which is x square by 2, and it will go from 0 to L, and the second part will be an integration from 0 to L. So there will be an x, and there will be cos n pi x by L. There will be an n pi x by L dx. Agreed? Now one thing what I'll do is I'll not solve this step. So let me tell you that this will go to 0 when you solve it, and you will be left with only L divided by 2. So what you see, for n equals to 1, for n equals to 1, the expectation value of x is indeed L by 2. It means most of the time the for n equals to 1 state, the electron spends at the center of the wall or the box of the 1D box. So what do you mean by n equals to 1 state? N equals to 1 state means when the electron in the box has the energy of only h square by 8 ml square. So whenever this electron has this energy, it means the electron is in the state of n equals to 1. It means if the electron is kept at this energy in the ground state, then most of the time the electron will be found at L by 2. If you increase the energy of the electron, then the probability of finding the electron will look like this. It means there is a maximum probability of finding the electron here, there is a maximum probability of finding the electron here, and there is absolutely zero probability of finding the particle at the center of the box. So that is when you increase the energy. Similarly, at various energy levels, if you go on increasing the energy of the electron confined in the 1D box, the probability distribution will change accordingly. Agreed? So we found the expectation value of x. Now can we find the uncertainty in x? Because you see, this is a quantum mechanical system, and we said that every quantum mechanical system has Heisenberg uncertainty principle inbuilt in it. Now question is, what is the uncertainty principle that this particular system follows? Okay, now how to do that? Okay, so the expectation value for n equals to 1 was what? L by 2. Similarly, what you need to do is you need to find the expectation value of x square. Okay, so how to find the expectation value of x square? You know that it will be an integration from 0 to L. There will be a psi star psi. So I'm writing psi square because psi star is same as psi, and there will be an x square into dx. Agreed? So you need to find this, and then the uncertainty in the position can be easily found when you put these values in this mathematics that we have already derived. So that is, put the value of expectation value of x square minus square of expectation value of x. Agreed? So this one, when you will calculate for n equals to 1 state, what you will get? You will get a value of L cube divided by 3 minus L square divided by 2 n square pi square. Okay, so in this manner you just put both the values in del x, and you can find the uncertainty in delta x. So when you put the values, you'll get the uncertainty in delta x as the L will come outside, and inside you will have root over of 1 divided by 12 minus, see, these are easy mathematics that you can do it yourself. So 1 by 2 pi square. Agreed? Now you can keep the n yourself if you want. The n, if you are solving for n equals to 1, then this part will have n equals to 1, and this part will look like this. If you are doing for normal n, then in the entire stuff with pi square there will be an n square. That's it, if you are doing it for normal n. Similarly, you can find expectation value, you can find the uncertainty in momentum. So what is uncertainty in momentum? You need to find first the expectation value of momentum square, and then you need to find the expectation value of momentum, and then square it, and then subtract both the term. Now what is expectation value of p? Okay, how to find? So this will be integration from 0 to L. So as I said, there will be a psi star. So what in between you have to keep? You have to keep the momentum operator. So what is the momentum operator? As we have discussed in our earlier lectures, it is minus IH cross del by del x. So into psi dx. This is the momentum operator. Expectation value of momentum. Now you need to evaluate this. So how to evaluate this? You need to put the value of psi star. We know that psi star will be same as psi. So this will be nothing but psi square. But this is not how you evaluate the integral. So how you need to evaluate is, so 0 to L, you need to make this act on the wave function first. So psi star is what? Psi star is root over of 2 by L sine, okay, n pi x divided by L. So keep it here, don't do anything, and there will be a minus I h cross. So keep it here. So what you need to do is now you need to make d by dx, okay, act on this psi. So what is our psi? So this is our psi. Agreed? And then there will be dx term in the end. So now you can easily evaluate this integral. Looks complicated, but at the end of the day you will get an answer. So what answer are you expecting here? So the answer, after you calculate the expectation value of momentum, will fetch you a value of n square pi square, okay, h cross square divided by L square. So these are some long calculations that you need to do it by yourself to look at the answer. Okay. Similarly, made a mistake. So this expectation value of p is actually 0. So if you evaluate this integral, you'll get expectation value of p is 0, and the expectation value of p square is actually this. Now question is, why do you get the expectation value of momentum as 0? So what is the physical meaning? Why do you get the expectation value of momentum as 0? Um, so as I've already discussed earlier, that by a clever choice of psi, okay, so by a clever choice of psi, you can always make either this as 0 or expectation value of momentum as 0, or you can also make both 0. And the clever choice of psi was actually in this case dependent on the clever choice of the coordinates. So here the coordinates was from 0 to L. So now, so there is an expectation, there is an uncertainty in momentum. So if you calculate the uncertainty in momentum, you will get the value of n pi h cross by L, n pi h cross divided by L. How do you get this? This is very easy. This part is 0, as we have already discussed, and this part is already calculated here, and just do the root over of this part. Agreed? So now you see that if you do the uncertainty principle, so if you do the multiply the uncertainty in position with respect to uncertainty in momentum, okay, so what is the product? The product is a big one, so it is n pi h cross, okay, into root over of 1 by 12 minus 1 by 2 pi square n square. And indeed the uncertainty product is greater than h cross by 2. Okay, so this product is always greater than h cross by 2. So h cross by 2 is the minimum uncertainty. Okay, and every other quantum system will have uncertainty product which is greater than h cross by 2, and this product you see has a value greater than h cross by 2. So even the uncertainty principle is also satisfied in the particle in a box. However, there are other problems in particle in a box. For example, what happens when you change the coordinates? Okay, so if you have this particle in a box, if you have this box and you took the coordinate from 0 to L, so now what you do is you take the coordinate from minus L by 2 to L by 2. Okay, so the moment you change this coordinate, it means there will be some change in the boundary condition. This change in boundary condition will be reflected directly in the wave function psi. In this case the wave function psi will be different. but the probability is going to be same. Please see that probability is a physical thing that we can see. Probability is a physical thing that we measure. That is, at a particular position, what is the probability of finding the object. So obviously, if you change the coordinate, okay, you have all the reason to tell yes, the wave function will change, but the probability is not gonna change. So for n equals to 1, the probability will be will have a graph like this. For n equals to 2, the probability will have a graph like this. So even though by a clever choice of coordinate, the wave function will change, but the probability will never change, because probability is a measurable quantity. We actually measure probability, and there is no reason why the probability will change, because you have only changed the coordinate. You are not changing the box. Okay, even the length of the box is same. You see, minus L by 2, the length of the box is L. So the probability distribution should never change. So what do you understand from here? So you understand that the same system can have a different wave function if you change the way you look at the coordinates, but all the measurable quantities like the energies, like the probability, they will not change. Obviously there is no reason for them to change. Agreed? So in the next lecture, so this finishes our discussion on particle in a box. Okay, so in the next lecture, we'll discuss about a particle in a finite box, and we'll also discuss about some scattering processes like the potential step. Okay, in our next lectures.